Welcome to topic 2.2. In this topic, you will learn about the calculation inside this chilled water system. Let's say from a BMS diagram, you have a lot of parameters. You have the temperature reading, you have the flow meter reading. How are you going to use all these readings to do your calculations? And at the same time, you're going to learn what is this chiller plant efficiency? What do we mean by kilowatt per ton? Okay, which may be a term that you have heard before. Okay. So before we talk about the cooling load, okay, there are some imperial units that are very commonly used in this industry. Okay, so you must know how to convert from one type of units into the other. So as we know, for heat energy, okay, energy usually or power, we always use this units kilowatts. Okay. But there's a more commonly used unit which is called R-ton, okay, refrigerant ton. So how are they related? Okay, R-ton. So 1 R-ton is equal to 3.517 kilowatts. Okay, 1 R-ton is equal to 3.517 kilowatts. So when they say this chiller is able to provide 300 tons of cooling, so if you want to convert to kilowatts, you have to multiply by 3.517. So usually, if you want to have a very quick estimation on, let's say, when you have a floor plan and you want to estimate how much cooling you need to quickly size up your AHU or size up the amount of tonnage that you require, okay, there are some rule of thumb. So for example, let's say an office area, how do we know how much tonnage do we need? So the rule of thumb, they actually have this kind of table to show you that, let's say for an office building and you have an interior, okay, you may require 1 ton, right, is able to cool down around 340 square feet. Okay, or 1 ton is able to cool down around how many square meter? So these are what we call a rule of thumb, without using very exact calculations. Okay, and each building, right, is very different because rule of thumb is based on floor area, but they never take into account of the building height. So if the condition is very different, for example, you have your climate conditions, you have your orientation, all these you have to consider. Okay, for example, east-west facing kind of room will always require more cooling because it will gain a lot of heat in the morning and afternoon. Okay, as well as you have to consider how much ventilation you actually introduce into the space and the kind of lighting you use, etc. So a more accurate way to estimate your cooling load is by using simulation software. Okay, so nowadays there are a lot of software available in the market that you can key in all the parameters. For example, your number of occupants you have, type of lightings you have, the orientation of your buildings, and it can generate out quite accurately how much cooling load you will need, how much cooling load is required to cool down your space. So for chilled water plant, right, the building cooling load can be calculated, okay, and verified with data obtained from this BMS, Building Management System. So Building Management System is actually a centralized location where you extract all your important information, especially the temperatures and the flow rate and the power consumption, etc. And with all these parameters, you can actually do some calculation to verify whether it is correct or not. Okay, whether your design parameters are all correct, etc. So let's look at the schematic again. So you may notice it actually, so for some of the BMS, right, it will go and calculate internally inside the BMS software how much heat is gained, how much heat is rejected, and what is the heat balance, what is the efficiency, as you can see from the right arrow, okay, all the different equipment efficiency, or the kilowatt per ton. So some BMS may only provide the temperature and flow. So all these you may have to calculate yourself. But nowadays, most of the BMS will do the calculation before display out for the owners or for the users to see. So how do they arrive at all these readings? This is what we are going to learn today. And you may notice all these arrows, okay, is actually showing you the header. Okay, so these two arrows that's being displayed now is actually display out the header temperature. So how do we calculate the cooling load? Okay, let's revisit this topic 1 again. Okay, so you may remember this formula, Q condenser. That means the amount of heat you reject at the condenser will be equal to the amount of heat you absorb at the evaporator plus the amount of work done by the compressor. Okay, first, let's look at this famous equation. Q is equal to mc delta T. Okay, you may have heard of this equation before. So, what exactly is this about? Okay, so let's say you have a pipe. I will use an example. You have a pipe. Okay, and over here, let's say you do some heating. Okay, you do some heating. So when the water that go in before passing through the heating coil is around 20 degrees Celsius, okay, after passing through the heater, okay, it becomes 30 degrees Celsius, okay. So from here, what can you get? You are able to get the delta T, okay. So delta T is a temperature difference between your inlet and outlet. So in this case, it is 10 degrees Celsius. The second information you need is how fast your water is flowing through. How fast is it flowing through? So let's say it is flowing at 1 liter per second, or okay, 1.5 liter per second. That is the flow rate. That is the flow rate. And third thing you need to take note is what kind of fluid is actually flowing through. Is it water, or is it oil, is it air, etc. Okay, so let's say it's a water. And as we know water, we have this term called the specific heat capacity. Okay, specific heat capacity. So different kind of fluid will have different kind of different specific heat capacity. Okay, so what does this specific capacity tell you? It is the amount of energy you need, okay, to heat up 1 kg of water or 1 kg of that fluid by 1 degree Celsius or 1 Kelvin. Okay, so that's the meaning of specific heat capacity. So if this fluid is able to will gain heat very fast, it will have a very high specific capacity. Okay, so for water, right, is a constant value is 4.19 kilojoules per kg Kelvin. Okay, so these three items, delta T, okay, the flow rate and the specific heat capacity, if you go and multiply all of them together, it will tell you how much heat is actually being supplied over here, or how much heat is actually gained by the water. Okay, so if we going to use this idea onto evaporator, as we know in a chiller plant, okay, let's say you have a chiller. Below is your evaporator. Okay, so we know that chilled water actually pass through the evaporator. So usually this part we call it the chilled water return. Okay, chilled water return temperature, let's say it's around 13 degrees Celsius. When it passes through the evaporator, it can cool down to maybe 7 degrees Celsius. So from here you can get the delta T. Okay, and the specific heat capacity of water is a constant value, 4.19 as I mentioned just now. And finally, you will need to check your flow meter. Okay, what is the flow rate of the chilled water? So the flow rate is usually given in liter per second, but you can use it conveniently for your calculation because 1 liter per second is equal to 1 kg per second, because the density of water tells us that 1 liter is equal to 1 kg. So we can conveniently use this value for your calculation. Okay, let's look at one example, then it will be very clear. So for example, you have 13 degrees Celsius and 6.4 chilled water supply temperature, and you are also given the flow rate to be 45.4 liter per second. How are you going to calculate the amount of cooling load, amount of heat that is being absorbed at the evaporator. Okay, you may want to pause the video and try it out yourself. If not, I will just go through the solution. So very simple. First, you write down the constants that you have, okay, and 45.4 liter per second is effectively 45.4 kg per second. So using this equation, mc delta T, which you multiply the mass flow rate with the specific capacity and delta T, you fill up all the values, you will get 1255 kilowatts. Okay, that is to say the water actually reject 1255 kilowatts of heat to the evaporator of the chiller. Okay, so that's the amount of cooling you provide to the water itself. So that's how you do a calculation for evaporator. So using the same idea, you can use this for the condenser side as well. Okay, because over here, your condenser water enters the condenser at a lower temperature and comes out at a higher temperature. Okay, so the leaving condenser water is always higher, maybe around 34 degrees Celsius. So leaving condenser water temperature, let's say it's 34. Okay, entering condenser water temperature, let's say it's around 29. So from here, you will have your delta T again. Your delta T maybe is around 5 degrees Celsius. Okay, and at the condenser water side, you will also have a flow meter. The flow meter, of course, will also tell you what is the flow rate at the condenser water. And with this value multiplied by delta T, multiplied by the same specific capacity, which is 4.19, you are able to get your condenser heat rejection, the amount of heat absorbed by the condenser. Okay? So similarly, let's look at one example. Okay, calculate the condenser load, or what we call a Q condenser, okay, in this example. So similarly, you are going to use M condenser water, CW, multiplied by delta T. Okay, your mass flow rate in this case will be 56.8. Alright, will be 56.8. Multiplied by specific heat capacity of water, which is a constant value 4.19, multiplied by delta T, which is the temperature difference before and after passing through the condenser. So you will need to take 34.4 minus 28.1. So that's the working. So the rest is just a calculation. And you realize that the condenser load is usually higher. Okay, it must be higher than your evaporator load. Okay, it cannot be lower than evaporator load. And you may have noticed also the flow rate. The flow rate at the condenser water side is always higher compared to the evaporator side. Okay, compared to the chilled water side. Okay, because you need to remove more heat at the condenser compared to the amount of heat you absorb at the evaporator. Okay. So that is on the load calculation, which we use a very generic thermodynamic formula, which is mc delta T. So remember our heat balance calculation that we learned in topic 1 before, which is Q condenser is equal to Q evap plus W com. With these two values, right, you are able to calculate what is the work done by compressor. Okay, because you have your condenser calculation from BMS, you also have your Q evap. Okay, your Q evap that we done in the first example. Okay, you have certain values. So these two, right, once you know, if you subtract them, you will be able to find what is your work done by compressor. So let's look at the previous two examples. Okay, using the answer you get in the previous two examples, you are able to find out what is your WCOM. Okay, and remember, work done by compressor, we are usually more interested in what is the power input. Okay, because power input is what you actually pay. Okay, what is it? What is the amount of energy you actually consume from your grid itself? Okay, So first, if you want to find what is WCOM, you need to take your Q condenser minus Q evap. Okay, so initially your Q evap is 1255. If you subtract them, you will realize your WCOM is 244 kilowatts. That is the useful work done by your compressor inside the chiller. Okay, but to find how much energy is actually, how much power is being drawn, okay, you will need to take into account of the compressor efficiency. So still remember the formula, Win is actually equal to WCOM divided by compressor efficiency. So if you use this same formula, you will take 244 divided by the compressor efficiency, which is given to be 90%. So with that, okay, you calculate out, you will get a power input of 271 kilowatts. Okay, so that will tell you what is the power input drawn from the, and you will see this value at your power panel, okay, the power meter. Okay, and they also ask for another thing, okay, what is the COP of the chiller? So if you still remember topic 1 formula, COP is equal to Q evap divided by W in. So Q evap we have 1255, okay, and power input we just calculate, which is 271, and with that you will be able to get your COP value. Okay, so all this equation is not new, all these formulas are not new, just that it can be applied over here, or it can be applied just like how you use your pH diagram, okay, how you use topic 1 kind of situation.